All right, hello everyone. Thanks for having me here at EdCon. So, as mentioned, I'm Doug Petkanics, founder of Livepeer. I'm going to give a technical talk today about how to scalably verify the results of computation that are done off-chain. We've talked a lot about on-chain scalability, but a lot of computations are very heavy, computationally intensive, and it would never be practical for these sorts of things to ever touch the blockchain. But you want to get the results of these computations back on-chain in a way where everyone can trust the output so that they can be used inside of your protocols. So a little bit of background. I'm going to talk about how we've built on top of a protocol called Truebit at Livepeer, where we work on peer-to-peer video streaming. We're trying to add a live layer to the Web3 stack for live video, live audio, streaming data, which is kind of a missing layer. What this can enable is video-enabled dApps and applications, auto-scaling services to pay-as-you-go for video streaming, pay-as-you-go for content, and the benefits of decentralization like censorship-resistant journalism, freedom of speech protections, and whatnot. So the type of computation that we have to perform in video kind of streaming is one video comes into a network from a broadcaster, and you want this network, this distributed network of computers, to make sure that that video can reach every device on the planet at every connection speed. There might be one video that comes in. You might need to convert it into up to 24 different renditions, bit rates, output protocols so that it can play on HDTVs, cell phones over 3G connections, smart TVs, browsers, etc. So the type of software that does this is called a media server. And these have been closed proprietary things that are aware of all the different codecs, video formats, bit rates. And what they do, like I said, is convert video. So the software that we're distributing is a media server to hundreds or thousands of machines across the network. And what they're going to do is encode video. And the question that you should ask is, if you're going to pay a network in Ethereum to encode and distribute your video, how do you trust or guarantee that this encoding is done correctly? You don't want your viewers to be watching blank output or illegal or illicit output of the video, because the file that comes in and the file that comes out are very different. But how do you know that the correct computation or the correct encoding was performed on this video? And I'm using video as an example, but this applies to any form of compute that your protocol might want to do. 3D rendering, scientific calculation, machine learning models and training. All of these should be applicable to scalable protocols for verifying work. So we have a bunch of options here depending on the degree of trust that you want to put in a third-party system. I think the first option that many people might be familiar with are oracles. You can basically pay this network to encode your video, and then you can have an oracle check to see if they encoded it correctly and report the result back on chain. And there are services that do this, like Oracleize, for example, which you can basically build a Docker container. They will deploy and run it, provide an attestation back on chain, and you can choose whether you trust that result. So in this scenario, which may be good for many use cases, you're essentially trusting a company on every computation to report the correct result back. And you can decide whether that's the right degree of trust for you. But remember, you're trusting a company that may or may not continue to be in business, may or not perform to their level of service. So can we do better? Can we move that trust kind of up the stack? So I think the next available option is trusted hardware. You may have heard of projects like Intel SGX or Town Crier. What trusted hardware does is it basically, there's a private key on a piece of hardware that can never be observed or tampered with if the implementation is correct. And then when you deploy code to that chip, you get a result out in a way where you can trust that the exact code that you wanted to run ran and was not tampered with. And here, again, these implementations are done by a company like Intel, but Intel is not able to basically observe or interact or have any input to every single computation that you're trying to verify. You're just trusting that they did the initial implementation of the chip and the process for fabrication and distribution was tamper-proof. And you're kind of trusting that process. But then once this hardware is deployed and out there on a number of machines, you can trust that the result that comes out is correct. So again, you're moving the trust off of a single company on every transaction onto a hardware implementation, which again is kind of baked in the whole business model being that this is tamper-proof. And of course, we trust hardware with a lot of the computations we do in a number of use cases. So then, this might be good for many use cases, but I would still ask, can we do better? Can we get economic guarantees that the computation you wanted done was done correctly? And here, I would point to a protocol called Truebit. Can I get a quick show of hands if anyone here is familiar with Truebit? Awesome. So this is a really cool protocol. I'm going to give a little bit of background on it because I think it's mind-blowing. So the way Truebit works is that you have someone, you submit a job, so we might submit a video encoding job to Truebit as a task. There's a solver who's an actor in the Truebit system. Anyone can be a solver. They perform this computation, and they report the result back on chain. Anyone else can be a verifier. They also check the computation, and if they want to, they can challenge the solver's solution and say this was incorrect. So far, this doesn't sound mind-blowing. Anyone can kind of develop the protocol. Here's the really cool thing. Truebit has a smart contract judge which can look at what the solver said the result was and the verifier said the result was, and it can determine with a guarantee which one was correct. So you don't actually have to trust the solver or the verifier. The smart contract will tell you who is correct. So you may be saying, how the hell can we do that? The smart contract could never do video encoding or scientific calculation. So here's the cool thing. Truebit runs as a WebAssembly virtual machine. And they break the task down into very, very small steps, just one step of computation in a virtual machine. So that step of computation is like an add, a subtract, a push, a branch, a jump, any virtual machine instruction. At every step of computation, the solver and the verifier hash the state of the machine. And then at the end hash of the state, that's the result of your computation. If the solver and verifier have a different end state, it means they disagree. If they have the same end state, the computation was the same. They started with the same beginning state. That's just the input to the problem. So if they disagree, what the Truebit protocol does is you can binary search the billion or trillion hashes in this computation to find the first step where they disagree. That means the previous step they agreed. They had the same state. So you submit that to the smart contract, and the smart contract, which is a WebAssembly interpreter, can run one single step, maybe an addition, a subtraction, a branch. And then after doing that step, we know the solver and verifier had different states. The smart contract knows which one was correct. And from there, it can equivocate. It can slash the one who was incorrect. It can do all the economics to penalize someone who acted incorrectly, reward the person who acted correctly. And that's, I think, mind-blowing and super cool. So the next question to ask, thanks, applause for Truebit. We work closely with them. They're making great progress. The next question to ask is, well, this sounds complex and expensive. We wanted to encode video, and the benefit of decentralizing this is that we believe we can do it cheaper than centralized alternatives by distributing it across idle hardware. If you have to do all these on-chain dispute resolutions, you have to do this judging, isn't that super expensive? And the answer is yes. Truebit is estimated to cost 5 to 50 times the cost of the original computation in order to use this network to pay for redundant computation. So for some use cases, that cost may be worth it. For our use case and for many, it's probably not. So how do we scale this solution? And that's what we've developed at Livepeer and Livepeer protocol. It's basically a way to scalably verify work. And the way you do it is we use Truebit as a black box, but rather than send the whole video encoding job to Truebit, what we do is we break the video into very small chunks, 4-second segments. A broadcaster sends it to the network transcodes it. Someone who did that work and wants to be paid for it can commit to thousands or millions of segments on-chain using one single Merkle root of hashing all the segment outputs. So they've committed to the work for hours of video encoding with one transaction. And then you can choose in your protocol, you can choose your verification rate. You can say, I want 1 out of 10,000 segments challenged, or I want 1 out of 1,000,000 segments challenged. At that point, after the commitment has been made, the protocol can randomly select which segments are going to be challenged. The solver has to provide proof of what their encoding output was for just that segment and invoke Truebit. So maybe 1 out of 10,000 segments are challenged. So instead of adding 50x the cost, you incur a 0.5% overhead in cost in order to use Truebit just for that 4-second segment. But you can get economic guarantees. If they place a big deposit, and if Truebit says they failed their computation, the penalty can be significant. It can be not just a penalty for failing a 4-second computation, but a penalty for failing 40,000 seconds worth of video encoding. And you can get the same economic guarantees in a cost-effective, scalable way if you set your parameters right. So that's how the protocol works. A quick update on Truebit's progress. They have a working implementation on a testnet. They have a WebAssembly interpreter on-chain. They have a metered WebAssembly virtual machine off-chain. At Livepeer, we've compiled FFPro, part of the FFmpeg project, into WebAssembly. We can submit a job on-chain. We can play this verification game. There are not yet Truebit incentives, and we need solutions to the hard problems like the data availability problem, which is also facing Casper sharding. So that's an active area of research that we're really excited about working on. But I'm really optimistic, because a year ago when we heard about Truebit, it seemed like science fiction, but everyone's been working really hard. It's coming. We'll be able to verify off-chain computations in a way we can trust on-chain very shortly. So I think that's super exciting. And again, this is not just for video encoding. It's for any sort of compute that can be broken down into steps and segments. So to just recap the options, you can run a centralized verification server in Oracle. You can trust hardware. You can get economic guarantees through Truebit, or you can use a protocol on top to scale computation. I think all these options are exciting and are going to unlock a lot of possibilities. So thank you very much.